Okay, so we know that if we have a continuous variable, we need to use X bar and R charts for statistical process control. But what happens if we have an attribute variable, right? A yes or no, or good or bad quality, right? So, we looked at attribute and continuous variables a lot during the semester. We hope you guys know by now what it is and what's the difference between them. So continuous, it's when we have a scale, right? And we have the last example where we have the numbers, we can calculate average and standard deviation and all that. And when you have attribute data, you're basically you only know if the product is good or bad, right? Or it's one classification or the other one. So in this case, the only thing you can do is a percentage, right? Or so there are two charts to do that. They're basically doing the same thing, but the difference here is the sample size. So if the sample size is variable, so it's every time that you're collecting data, you're collecting a different sample size. That's called a P chart. And if the sample size is always constant, is always the same that you're collecting, like the example that we see with the X bar and R chart, that's called an NP chart. And I know that the definition is different than the core operations management course that you guys have seen it. But let's focus especially on an NP chart, which is what probably you guys saw on that core operations class, okay? So here are the formulas for them. I will go over them, and then we're going to do a problem with the NP chart. So again, it's a binomial distribution. It's only a yes or no. You only pass or fail. So we're looking at the proportion of products that have quality, the proportion of products that have defects. And again, the only difference is one I used with sample size is the same, and the other one is not the same. So this is the NP chart. As you can see, I collected 15 samples. They're all of 100 each one of them, so they're all the same. So that's why I'm using NP chart. 15 samples, and is 100 for each one of them. Here I have how many were defective, so total 55 defective. And what is the P for each sample? What is the proportion and the percentage for each one of them? It is here. And then I can calculate P bar, which is the sum of P, which is the 55. You guys remember this 55. So the sum of P is 55 divided by K times N. K is the number of samples and is the number of items on observations in each sample. So you can see here, K is 15, N is 100, and our P bar is 0.037, right? So that's the average percentage, right? They're going to be our central line. So that times 100, which is the sample size, it's 3.7. So our central line is 3.7, as in this case was defective products. So now to calculate upper and lower control limits, it's NP, which is that 3.7 plus 3 times the standard deviation. And this nasty part of the formula here is the standard deviation, the square root of NP bar times 1 minus P. So we know that NP is 3.7, and we know that 1 minus P, so it's 1 minus 3.7. So we get to our upper control limit here, 9.36, and these are in a number of defective products, right? Not in the percentage, in number of defective products. For a lower control limit here, NP, just kind of follow the formula, but it's a negative number. We cannot have a negative number of defects, so we're going to truncate it to 0. Okay, so upper control limit 9.36, lower control limit is going to be 0. Now we plot. You see that these numbers here are the average of the samples. So here the P's. So we put all the P's here. We have the upper control limit, the 9.37. We have the central line, and we have the lower at 0. The question is the process under control? Yes or no? So we know that if it's within the limits, it's under control. If it's outside the limits, it's not. So in this case, it is within the limits. So the process is under control, okay? So I'm gonna do this problem with you guys after this video. So now, after this video, you can try to do this problem here. We have all the formulas and we have the table with the data as well. But before that, I will just kind of explain the difference between the P chart, okay? So in this another example of, some defective returning product from the supplier that we're evaluating our supplier here. And you can see the difference here is the samples are here, but you have different sample sizes, right? And then you have, of course, the defects that we encounter, and the percentage of defects is just this divided by this is here. But you can see that because it is a different sample size, we cannot use the same formula, right? So sometimes you have more, sometimes you have less. The limits will change because that the number of data that you're collecting is going to change. So the formula basically is for each one of those observations, you can have a different range because of the different sample size. So if you collected more data, for example, you have more precise information, so your limits are far apart. If you have less sample size, your limits are close together, right? So it is different here by sample size. We're not going to do problems with this, but you guys have to know what it is and what's different. So now go back to problem 1 and do this problem, and I will, in the next video, I'm gonna do the math for you guys.